points of the application and start disassembling them. And whenever they find branching instructions, they usually put them into a queue and process them whenever they finish with a sequential part of code, right? Whenever they find like a unconditional jump or a red, they know, okay, I'm done with that chunk, let's see what I have in the queue. And then as you disassemble, you keep adding all the conditional jumps, all the calls, whatever, into that queue, so eventually you process everything that is referenced from the code you started from. You can try to disassemble a little bit further, but like disassembling after reds and jumps, you know, might or might not be code, so you have to be a bit careful with that. So the problem is, depending how you handle this queue, just imagine, just disassemble sequentially, you find a conditional jump. Okay, you can start disassembling after that conditional jump. Normally there will be proper code. But if the conditional jump is always taken and goes somewhere else, that overlaps over that code. That's what I'm going to explain a little bit. It's complex because if it overlaps, if you take one branch, you see one kind of code. If you take the other branch, you see another kind of code because it overlaps. Only once is going to be taken in the end. But it actually leads to different code. So for an analysis tool, that's hard to decide. You know, if one is obviously non-code, yeah, you can say, okay, I'll drop that. But it might not be totally obviously non-code, so it's hard to decide. And so it results in confusion for most tools. So one of the things that IDA makes is really powerful is that it's interactive. So you can decide when you are analyzing what is what. Well, other tools, you cannot really do that. And only you really have to go there and tell it to analyze a specific part, while IDA is a little bit more versatile into that. And then another side effect, this is not necessarily a tool for obfuscation, but it works like that, would be heavy optimization. And I'll just have an example of that later on, which nowadays compilers, if you go to extreme levels of optimization, make the binary really, really nasty to look into. So one thing that, if anybody has looked at ASPAC, that just like comes like at the first thing at the entry point and goes a little bit into this decidability of what branch to take, right? So if you disassemble this sequentially, this is the original set of instructions, after the call, and you know, normally code follows after the call. So you want to continue disassembling, it's not a non-terminal branch. Normally call returns and there is something after that. So if you disassemble sequentially after the call, there is a jump. But the jump goes not really anywhere, it's an invalid address. But you see this +1 in the end. That +1 means that it's jumping into the next instruction +1 byte. But the disassembler in this case, either the last version actually handles this properly, but in the older versions didn't. So if you disassemble this sequentially, which would be one of the most obvious things, you see that this call doesn't look too nice. So the right way of disassembling this, but it's hard to say unless you know it works like this, is just like not disassembling the next instruction and going to where the call points to, and that's the real instruction, and that's a proper jump. So that's one of these anti-analysis techniques that actually is aimed against the analysis algorithm of the tool, of the disassembler in this case. Another case would be this linear disassembly. Again, we have a similar case, jump +1 instruction. If you follow straight, you'll disassemble the jump. Here you will have to leave, jump over that instruction to get to the final destination. A more interesting case, though, is the opaque predicate, because again, we're a little bit like in the case of the call. We cannot decide after the conditional jump whether to follow one branch or the other. So if we continue disassembling after the first conditional jump, we get into another conditional jump which looks like it should be the real thing. But if we actually would follow the reference first, we'd actually get to that move, which is the actual real code, jumping over that thing. And as you can see, the condition always evolves to true, so you will always take that jump. So when you use all these techniques all over the binary, make the flow a little bit annoying to follow, as you can imagine. And some of the packers use these techniques, reassembling binary code using this all over. So you get like really small functions blown up to something really large where the actual flow is really obfuscating, and most tools cannot follow it properly. So even it's really large, it's not even contiguous. You have to make a lot of manual work to get it to look nice. Then moving on to the side effect of heavy optimizations, this would be like normal functions looked in a normally compiled binary, where you would have a function in a contiguous area of memory. You would have all the chunks, all the basic blocks of the function, always together. But if you use heavy optimization, if you use what is called profile guided optimization, so that the application is compiled first with instrumentation, is run over a certain time with the common use cases, and that statistical information is used to later on compile the application for the commonly traveled areas to be together in memory. That saves time because all those blocks will be together in memory. It needs less paging, it needs less cache in the CPU because all of these frequently touched basic blocks are all together. Then you will end up like in situations like this, where a function is split all over the file. Most tools won't have a problem if you're working with the graph view in IDA. It will pull the chunks wherever they are in the binary and show them together. But if you're in the text view or in any other disassembler, you will have a basic block, you have a reference some other place in the file with the next basic block, so it makes it kind of annoying to work with. And that's just a side effect of optimization. Then further optimizations, which I've seen in the Microsoft compiler in their own binaries. I haven't managed to get these working with the official version of the compiler, which is the case when you get shared basic blocks. When the compiler started doing all this splitting, it actually realizes too, in some cases, that the ending of some functions is the same. So instead of repeating those last basic blocks, it actually points different functions to the same set of basic blocks, which is usually just a couple of basic blocks restoring something or doing some error notification and returning, because well, it has to be the same flow for both functions. But again, this is really annoying because at least I think to one of the last versions, the algorithm cannot assign certain basic blocks to more than one function. So you will get blocks that are split but won't appear in some functions view. So you will get missing parts of code. Well, not missing. If you follow the reference, you get there. But the logical view is not necessarily totally correct. And this is not necessarily a technique made against analysis, but it just happens to make it a bit harder. Then we move into the addition of polymorphic and static junk, and we will see that in a case in Temaida. Good hints of finding junk usually is like the push A and pop A. These instructions save all the registers and restore all the registers from the stack. So it's used commonly whenever they insert junk to save the state and restore the state of the CPU. And so they will just like store it or save it and put a lot of crap in the middle, like 2 instructions, whatever, so something that looks like it could be code. So the analyst cannot tell it for sure whether it's junk or not. And then in the end, towards the end, do a pop A. That's the easiest. It's kind of easy to tell that, you know, there's something like that going on when you see those 2 instructions. And then as well for junk code, or it's still very annoying, will be the constant branching. Like I've seen obfuscators that take a piece of malware, take a function in a piece of malware, and they will get every single instruction, put it in a place of the binary, do a jump through a table to the next instruction in that function. So you end up with like function, it could be like 20 instructions. With all the instructions split all over the binary, it will jump. So it's really annoying to look at that because you don't see it contiguously at a single time. So as an example of this obfuscation, this is a small chunk of Temaida. And Temaida is like breaking obfuscated functions all the time with jumps. So in this case, you can see there is a deck in the beginning, there is a push all, so it's saving all the registers, then it moves something into ECX, push ECX, then saves the flags, then jumps somewhere, which is in the top here, jumps to a jump that then jumps somewhere else, and that somewhere else, the only thing that restores the flags, pops ECI, and then pops all, overwriting ECI. So all of these did nothing other than jumping around, except the first deck that decremented EAX by 1. But the rest, nothing happened. So whenever you get lots of these, and you get lots of this, it's really, really annoying to look at the code. In some cases, it's more or less obvious. In this case, you could even script it, finding the equivalent number of pop-alls, push-alls and pop-alls, so that you could try to decide, okay, I've seen the same number of things, nothing happens in the middle, there is no memory writes, so I could just like optimize all of this out. But in some other cases, it can be a little bit more complex to decide whether it's junk or not, so like, at least within the script. So that would be like simple examples of junk code insertion. And these obviously can be polymorphic. You can have certain routines that generate these do-nothing operations, so in every run of the application it looks different. Then moving into what has become lately the more fun part to work on with malware protection, which are virtual machines. And virtual machines, it's a relatively old idea, and their implementation in malware doesn't really bring anything that much new. except that it makes it really hard to analyze. So virtual machines, they exist in Visual Basic, Java, Python, Ruby. It's basically you get a language that gets compiled to some sort of bytecode, and that bytecode gets interpreted. So protections using these are StarForce, VMProtect, the x86 virtualizer, which is a really nice example because you have the source code for that in OpenRC. So the x86 virtualizer, it's like full virtualizer, uses lots of really nice techniques, and you have the full source code, so you can, it's really interesting project to look into if you're interested in understanding well how virtual machines work. And then obviously Themida and Cold Virtualizer, which are famous within the malware world just because they work really well and make the analysis a little bit nasty, a little bit hard. So the basic working of this is the code gets compiled or transformed into code for the virtual CPU, and what you end up seeing in the malware is an emulator or the implementation of the virtual CPU that will go fetching all of the virtualized instructions and executing them. So you will see these like abstract CPU running, but you won't see the original application. Well, that too, but on a different abstraction layer. So it makes it really hard to comprehend an application. What you're seeing is the virtual machine running, getting an instruction, processing it. Doesn't make it much really obvious. So basically, all of them end up being like a fetch the code and handle algorithm, and there are certain patterns that you can see on the virtual machines. The idea would be something like this. In a normal application on the left, there will be the standard code running on top of the real CPU. That will be the assembly code you see when you disassemble the application. So it makes it really, really easy to see, to just read the assembler, that's it. For a virtualized application, you will get the virtualized code that would run on a virtual CPU, and that whole environment emulated would run on the real CPU. So what you are seeing is the virtual CPU emulating stuff. And the general layout of this is pretty much generic to all the implementations. The virtual CPU, that will be the program that runs, at some point will get passed originally in the beginning a pointer or indicator to where the virtualized code starts. And then it will go and fetch that instruction. It will usually uses the opcode to look in a table where the handler for that instruction is, where the actual code implementing the instruction is in memory. But these opcode tables can be, at least Themida encrypts the actual opcode to reach the table, so it won't be obvious finding the opcode. In something like, for instance, Visual Basic is really obvious. If you want to study the virtual machine, you'll find a whole, like a really huge table of pointers, and you will see that it's really easy to find where it's going next. In a case like malware, they try to obfuscate that as well. So, but the algorithm behind all of that ends up being simplified, something like this. It will go find the opcode, find where the decoder will find where the actual handler is. The handler will actually perform whatever operation it has to do, update whatever registers it has to do in the virtual CPU, and then the decoder, after the instruction is finished, it will increment the instruction pointer to go to the next instruction. But that will be the red arrow there. So it will basically go through all these numbers all the time, executing all the virtualized code. So that's the process you would see in the assembly, which again abstracts a lot the actual application. So the attacks or the countermeasures you can actually try to implement against virtual machines, although it's a really, really hard field because there is no generic technique against all of the virtual machines, because each virtual machine can be implemented in a different manner, can implement a slightly different architecture. Take for an example Themida. Themida, when you pack an application, lets you choose between like 4 different types of processors, 2 CISC and 2 RISC, and all of them can have their opcodes randomized, polymorphic, so every time it runs it's different, like the slightly different architecture. So generalizing all of that at a high level so you could actually attack all of those, all of the virtual machines implementations, is hard, to put it mildly. So what some people have been doing, Rolf Rose actually has some really good articles in OpenRC, is translating the actual code, and actually Borislav actually was working on something very similar, had a really good paper. I have all of that in the references. So what you can do is translate the virtual machine representation. You need to study the instructions, you need to study all the handlers to know what they do, but translate all of those to an intermediate representation, and then use normal compiler techniques to optimize them. So eventually, and that's a technique you can use on the same lines against junk code, just translate it to something and optimize it. Eventually you will get a more or less canonical representation of the actual meaning, and most of the garbage will get optimized out, because eventually they will be adding and subtracting to the same register, or they will be modifying registers that will